So, as we've just first I'm Ben Taylor, to chat to you about a bit of work I've only recently just started and kind of finishing on looking at quantifying the stock of carbon in the salt marsh of the Estuary, as we've already been introduced yesterday by John, and just now by Rebecca. Like carbon, blue carbon is buzzwordy right now. Let's start this talk by saying this word preliminary right here. It's quite important for this one right now. The samples are hot off the presses, taken at the furnace on Monday morning, so it's thoroughly up to date. So first off, as we've just heard, carbon is quite an important thing. Ecosystem service at the moment in salt marshes. They potentially are huge sinks, deep, long-lived, continually accumulating sediments, much like the Merle, where you can get this build of carbon over time. There's reduced decomposition of that organic matter within those sediments, and so at the moment, peatlands are also a big thing. Potentially one advantage of salt marsh restoration is that there's minimal methane production, whereas peatlands potentially produce methane, which is another greenhouse gas. So I have been assessing the way in which restoration has or is altering carbon storage on the Estuary, and what does this mean in quantifiable benefit of carbon storage, and what drives these differences between the natural area, the mudflat, and the now restored marsh, which has been converted and enhanced, as it were. So, where is this? So, for those of you who know, the Eden Estuary is just north of St Andrews. I assume everyone knows where that is. This is for the people that are on the internet. The top right of the picture, the bit of green, that's a golf course. On the left-hand side is an army base. And the estuary itself is quite small. The study's been done here because over the past 15 years or so, a bit longer than that, restoration activities have been going on the estuary. So it's quite a nice system that it's quite enclosed, it's quite small, there's mudflat, there's natural marsh, there's restored marsh. So it's all in this nice little unit. So 3 areas that I've sampled within this red zone, healthily located, are the natural salt marsh, restored salt marsh, which is done through transplantation of bulbochinus marsh. So this is taking healthy stands of bulbochinus and marsh, kind of a rushy type plant, breaking that down, replanting in a lower density fashion, and allowing that to help extend existing marshes or generate new marshes in front of old upper marsh and then adjacent mudflats to have a business as usual value. So this is where that red circle is highlighting. This is an aerial image. You can see the golf course, the bottom right hand half of the picture, then the salt marsh, and then the mudflat. And those are the areas that we've studied. So we've done, mudflat is within, the maximum extent is 50 meters out from the salt marsh, and it doesn't approach within 20 meters of the salt marsh. So it defines being mudflat, close up to the salt marsh, but not so close that it's going to be, any data we get is going to be definitely mudflat environment rather than salt marsh environment. For the natural marsh and the restored marshes, the exterior extent was mapped, and then I put a buffer of 3 meters within that. So I'm not sampling right on the edges of these systems. I'm getting a value for what is the system itself rather than the transition area. So there was 5 random points were selected within each of these areas to take some sediment cores that you can see here. So coring, I managed to get hold of a vibrating core unit, being demonstrated here by Dave. Isn't it? Great. He's clearly disappointed. And so it's a 3-inch tube, and the idea was to go down to a meter if we could, or down to refusal, so as deep as we get the core. The benefit of it being vibrating, there's less compaction in theory, and the size makes it easier to get into, especially the denser salt marsh sediments where there's rooting material, etc., and it causes a vacuum, so you lose less out at the bottom of the core. And then these cores are frozen and removed by defrosting the outside of the tube quickly and then vibrating the core out. We get a nice solid block. Again, minimizing any disturbance or distortion to the core, so we can get nice, when we're slicing the layers, we're getting accurate depths. So I've done 1 centimeter sections, 0 to 10 centimeters, 5 centimeter sections, 10 to 30, 10 centimeters, 30 to 50, and then 25 after that. This is, if I could do 0 to 10, the whole thing, that'd be great. It takes a long time. I don't actually have any money for the analysis of this, so I'm still acquiring that. So kind of money constraints mean that I can't do it all fine scale, but the more dynamic, potentially more dynamic layers have been sampled more intensively. So I've done 3 cores for you. 1 from the mudflat, 1 from the restored area, 1 from the natural area. These are the deepest cores we got, and obviously pinch of salt, because this is just 1 core each. But we're getting some good data. So the mudflat on the far left is showing a low percentage carbon content down the entire core. The green of the natural area is more to the right. It's a bit switchy, but as a general rule, the general pattern is higher carbon content. For the restored area, it kind of sits in the middle, which is great. I wasn't expecting it to be as different from the mudflat lower down. If it's to be straight, the top 10 centimeters maybe would have had this enhanced carbon content due to restoration, but there's something going on which is potentially extending that benefit. So that's good. That's a lesson in not altering your talk straight before you give it. Sorry, the graphs have gone. That's fine. That's right. There'll be another graph. So here's another graph. So this is just an average of that same data that I've just taken. So I've averaged the 0 to 5 data, 5 to 10, 10 to 30, 30 to 75 centimeters. And so we can see that as we move deeper, there's a general trend of reducing carbon content. In restored areas, if we compare the restored area back to the natural marsh, we can see that they are somewhat similar, and the mudflat is definitely on its own far less. Now, the restored area was mudflat 10 years ago. So something has happened, potentially, obviously huge caveats on that because these are just 3 cores. But something's going on, and it looks like we are gaining more carbon, storing more carbon in these restored areas than we were previously. So that's the carbon aspect. If we move on to organic content, which you naturally assume would follow carbon content, and it kind of does, but not really. There's a straight. I haven't looked into it, but so there's not a huge correlation between the amount of carbon content in these cores and the organic matter content. So for these, there were subsamples. So I took 2 grams of sediment from each slice, ground it all up. So it's just sediment, no roots, nothing else. Threw some in an elemental analyzer, and then the rest of that sample I combusted for organic content. So they come from the same tiny subsample, and they don't correlate particularly well. And if we look at the graphs, suddenly the restored area, in terms of organic matter content, is far more similar to a mudflat. What this means, I am currently not sure, but for whatever reason, the organic matter that is in the restored area is more valuable, has a higher carbon content than the organic matter that we're finding on the mudflat, which is great. That's still good, but strangely, the pattern does follow more or follow well with water content. So this is to do with roots, biomass in the restored areas. As I say, as yet I'm unsure, but part of the ongoing work will be to separate out the rooting biomass and get a dry weight for rooting biomass and the dry weight for the sediment. So that's good so far. Kind of the general pattern we're looking for is there. We're getting more carbon stored within the natural marsh, slightly less in the restored areas, but definitely there's been a shift from the mudflat. So let's do fancy things like Rebecca just did and see how much carbon there is in the salt marsh. Again, before we tweet that restoration of salt marsh is going to fix climate change, this is 3 cores, and perhaps don't tweet this. Tweet the talk was great, but not this bit. So again, this is huge assumptions, but I thought I'd show you anyway. So if we generate a carbon density value, so we've taken the bulk density, we've taken the carbon values for each slice, we've generated a carbon density in each area, so the profile for each one. So we see the restored area and the natural marsh start to overlap more, because the bulk density in the restored area is higher. So therefore, there's a lower carbon content, your higher bulk density, pulling up your contribution, I guess. So that means that just on that one bit patch of salt marsh that was sampled, it's looking at 220 megagrams of carbon within that marsh, so that big green line. And in the restored area, just the restored area on that south shore, not in any of the restored marshes over the estuary, 7 megagrams of carbon. And if we look at the red and the brown bars, the brown bar I've calculated using the same area as the restored area to highlight. So the mudflat was there before the restoration. So if the restoration wasn't there, that is a value we should expect. Then the restoration is there, we can prove additionality. So from an ecosystem service point of view, more importantly from a payments for ecosystem services point of view, you're proving additionality that extra carbon is stored there, which is valuable. That's fine. Just stored there, which wouldn't have been there before. Which, from an economic standpoint, is something you have to be able to say. Otherwise, it's like people say, "Well, I'm going to pay something that would happen anyway." So, further, in terms of total carbon storage within that patch, just looking at the marshes, obviously the natural marsh dominates. It's kind of a huge amount. It's so much bigger in extent. If we correct that by area, within the 10 years it's been there, restored areas are punching like for like as a natural marsh. Functionally, they are storing the same sort of equivalent amounts of carbon as a marsh that has been there for hundreds of years, which is great. So that means that in theory it's working. As we restore, we could say that within 10 years, functionally, we're storing carbon as efficiently as a natural marsh, which will continue to, and the restored area will continue to accumulate over time, which is lower in the tidal frame than the natural marshes. So what next? As I said, I want to calculate actual bulk density values for the sediment, excluding roots. I look at the distribution of roots down the core to give an accurate carbon biomass value for the plants. And obviously do particle size composition and hopefully do some aging. Get to chat to you later, Becca, because it'd be good. It's very expensive, or from what I've read, it's very expensive. It'd be really interesting to know how long the natural marsh has taken to get to the state it is, so they can forecast for the restored area. Cheers. Any questions?
Thank you, Ben. Any questions from the floor? John?
Thank you, that was really interesting. It's good to see more results coming out of the PhD. The one thing that really struck me about your graphs was the dramatic drop-off in carbon content from the marsh, between 40 and 50 centimetres. Any idea why that is happening?
I am hoping that it's because we're getting down to the mudflat level. So obviously, historically, it could have all been mudflat, and then vegetation is colonised and grown. So hopefully, when I do particle sizing, when I get down to 40, the particle size composition will match that of the mudflat. Down the core, when I'm when samples are ground, there's definitely a difference. Like, you can see the difference in the particle size. I think it's probably something linked to that. Has anyone got any other insights?
Great, thank you. In the interest of time, we will leave it there. Thank you, Ben.